Tech in 5.
Python in practice, master real-world projects in 5 minutes. Ever curious about what goes on inside a neural network as it learns to recognize patterns? Welcome to Tech in 5, where today, we're unlocking the secrets of neural networks, such as how these powerful models learn to recognize patterns. Neural networks might seem complex, but at their core, they're about transforming data. Today, we'll delve deeper into the neural network model we introduced in our last video, used specifically for digit recognition. We'll explore how it's set up, how it learns from data, and how this learning empowers it to make accurate predictions. Now, let's take a closer look at SimpleNet, the neural network model we've used to recognize handwritten digits from the MIST dataset. SimpleNet is structured with 3 main components: the input layer, the hidden layer, and the output layer, each playing a crucial role in processing information. First up, the input layer. It's where all our data initially enters the network. For the MIST digits, each image is flattened from a 28 by 28 pixel grid into a 784 element vector. These elements feed directly into the input layer, which doesn't perform any computation, but serves as the entry point for our data into the network. Next is the hidden layer, the core of our network where most of the computation takes place. In SimpleNet, this layer transforms the input data using weights and biases, adjusting them through training. It includes a ReLU activation function, which introduces nonlinearity, enabling the model to learn and represent more complex patterns. Finally, the output layer. Here, the transformed data from the hidden layer is compiled into 10 nodes, each corresponding to 1 digit from 0 to 9. This layer uses a softmax function during prediction to determine the probability of each digit, effectively deciding the most likely digit represented by the input image. Each layer of SimpleNet is intricately designed to handle specific tasks, from data intake at the input layer to complex transformations in the hidden layer, culminating in the decision-making at the output layer. Now, let's see how our neural network processes data during what's called the forward pass. This is the first phase of training, where data flows from the input layer through the hidden layers and finally to the output layer. As data passes through each layer, it is transformed by weights and biases, which are essentially the network's parameters. But the real twist comes with the activation functions, like ReLU, which we use in our hidden layers. These functions introduce nonlinearity, enabling the network to learn and represent complex patterns, far beyond what a simple linear model could achieve. Without these functions, our network would struggle with complexity and could only form straight-line relationships. With them, it becomes capable of understanding the intricate details of handwritten digits. Once our network has made a prediction, it's time to learn from it. This learning phase starts with calculating the loss, which measures how far the network's prediction is from the actual truth. Minimizing this loss is crucial. It's how the network adjusts its weights to improve. We calculate gradients of this loss with respect to all weights in the network, a process known as backpropagation. Backpropagation is like the network thinking back through its decisions, understanding where it went wrong, and tweaking its weights slightly to make better predictions next time. After training, our model is ready to take on real-world tasks. When a new image is fed into the network, it uses the weights it has carefully adjusted during training to analyze and interpret the image. The final output is determined by the output layer, often using a softmax function for classification tasks like ours. Softmax turns the final layer outputs into probabilities, each indicating the likelihood of the image belonging to one of the 10-digit classes. This probabilistic output helps in making a definitive prediction about the digit in the image, showcasing just how intelligent our model has become through training. And that brings us to the end of our deep dive into how neural networks transform data, learn, and make predictions. We've seen how these networks turn raw data into insightful predictions, helping machines understand the world a bit more like we do. Stay tuned for our next episode, where we'll explore even more advanced topics in machine learning.
Stay tuned for more videos on Tech in 5.